Good morning, girls. This is the second video of chapter sound. So in last videos we already discussed that how we represent the equation for displacement of sound and the terms involved in that particular equation. So now see here, there is a relation between velocity of wave, frequency and wavelength of a particular wave. This expression already you got in class 9, but there is a just like revision. I have written the formula here that velocity of a sound wave, which is v. Generally in this chapter we are discussing sound wave, so that is why this v is the velocity of sound wave, which is equal to the product of wavelength of the wave and its frequency. Now, what is wavelength of a wave? So remember that whenever we represent a wave in this way, this is called the crest of a wave, and this point is called the this is called the crest of a wave, and this point is called the trough of a wave. And the distance between two consecutive crests or the distance between two consecutive trough is called wavelength. Okay, that means from this point to this point, this much length is wavelength, that means lambda. But apart from this definition also we can find out wavelength. How to find out a wavelength? Let us focus on this diagram, this diagram. Okay, see here, as I told you that crest to crest is one wavelength, or trough to, there may be another trough, so trough to trough is again the definition of a wavelength. But if you start from this point, then at which point will you get the wavelength? One wavelength at this point. That means wherever the wave completes one cycle, there we get a wavelength. See, from this point if you start, this is a semicircle, means half of a cycle. This is half of a cycle, so it is completing a full cycle. At which point? At this point. So that means this is also lambda. Okay. When we discussed this wavelength in terms of crest and trough, then also you have seen, probably you have noticed that there also it completes one cycle. See, from here if we start, as I said that from this point to this point is one wavelength. See, from this to this part, this much, that is half of a semicircle. From this part to this part is half of a semicircle. That means this is half of a semicircle, this is also half of a semicircle. It is forming one semicircle, and this is another semicircle. So isn't it completing one cycle or one circle? So if it is completing from this point to this point, if it is completing one circle, that means this much length is also wavelength. Okay, so I hope it is clear. In fact, the same thing you can use if you move from one trough to another trough, then also it will complete one full cycle. Then frequency, this one, nu, we represent it by nu. Then frequency means it is suppose there is a wave and this wave is traveling through this point from this is a region, and through this region this wave is moving. Frequency means within 1 second the number of wavelength passing through this region, number of wavelength. From here to here one wavelength, from here to here another wavelength. So how many this is, suppose this is one wavelength, another wavelength. So within 1 second through this particular region, how many waves are moving? That is the frequency. Suppose in 1 second how many wavelengths are moving? Suppose 5 wavelengths are moving within 1 second, then the frequency of the wave will be 5. In that way we calculate it. Anyways, you remember this relation, v equals to lambda nu. Okay, the next topic is Superposition principle of waves. So superposition means it is overlapping. So it is said that resultant displacement of a particle at any point is the sum of the individual displacements caused by two or more waves at that point. Suppose we consider a medium and a particle or a point in a medium. Through this medium many waves are traveling. Suppose through this point also many waves are traveling. Suppose this is a wave passing through this point, another wave passing through this point, another wave passing through this point, okay. So in this way, if many waves are passing through this particular point, what will be the displacement of this point? For one wave, suppose the displacement is y1. We have the equation for y1, a sine, what was that, kx minus omega t or kx plus omega t, okay. So that is the displacement caused by one wave. Suppose y1 is the displacement caused by one wave, y2 is the displacement caused by another wave. So in that way, if n number of waves are passing through this point, the total displacement of the point will be vector sum of the individual displacements caused by individual waves, okay. So according to superposition principle, what we can write is the resultant displacement of that particular point is y, which is equal to y1, y2, in that way till yn, and the vector sum, this is a vector sum, okay. Displacement is a vector quantity. Then this is superposition principle. The next one, factors affecting the velocity of sound in air or gaseous medium or gases. Factors, that means we know that velocity of sound, the formula just now we got, v is equals to lambda nu. Then this velocity, it depends on some factors. So here we are discussing about the factors which affects the velocity in which medium, in air medium or in gaseous medium, okay. The first factor that I have written here is density. It is represented by rho. How velocity depends on density? This is the relation. That means velocity is inversely proportional to the square root of density, okay. That means if if rho increases by 4 times, velocity will decrease by 2 times. It is inversely proportional. So if one increases, the other decreases, and it is square root of it is inversely proportional to square root of rho. So square root of 4 means what? 2, okay. Similarly, if the density increases by a factor 9, density is increasing by a factor 9, velocity will decrease by a factor 3. Square root of 9 is 3. So that is the meaning, okay. Next one, humidity. So I have written here, greater the humidity, higher is the velocity of sound. Thus sound travels faster in a rainy day, because we know that in a rainy day the moisture in air is more, that means the humidity is more. So more the humidity, faster or more is the velocity of sound. So the sound wave will move faster in rainy day. This thing also you can explain from this formula. Suppose in rainy day moisture is more, means humidity is more. If humidity is more, that means in air we have more water particles. If water particle is more, air particle is less. Can we say that the density of air particle is less than? If density of air particle is less, what will happen to velocity? How they are dependent? Inversely. So if density of air particle is less, velocity of sound will be more. That is why in humid or in a moist day, since water droplets present in air is more, the air particle present is less, that means density is less. Density of air is less. If density is less, velocity of sound will be more. That is why the sound travels faster in a rainy day. Okay. Next two factors are there. One is temperature. So it is directly proportional to square root of temperature. Velocity directly proportional to square root of temperature. Capital T I have written, that means it is in Kelvin scale, not in degree Celsius. It is absolute temperature. Next one, pressure. Pressure has no effect on velocity of sound. Important point, that pressure does not affect the velocity of sound. Okay. Next one. Next topic is stationary or standing waves. If you remember, in last video we discussed about progressive wave, and there I told you progressive wave means there should be a source of the wave. From this source the wave will originate and it will move till infinity. We don't know where it will stop. It is moving, it is progressing with time. Okay. But standing or stationary wave means this wave motion, it will be confined between 2 points. Suppose between this point and a particular point, it will be confined. It will be stationary. It is not moving with respect to time. At some point it will stop. That is standing wave. And how this standing wave can be achieved? So for that, generally the reflection process or reflection phenomenon of wave is used. Now, about reflection you have already studied in class 10. There it was reflection of light. There were two laws. Okay, angle of incidence is equal to angle of reflection. Then incident ray, reflected ray, and the normal drawn at the point of incidence lie on the same plane. So here also when we discuss about sound wave, these two laws will be certainly followed. Okay. Now let us see how reflection produces standing wave or stationary wave. Suppose here we consider a string, that is a rigid support, and this is a string. The string is attached between two rigid support. Okay. And if the string is allowed to vibrate, then what will happen? From this point, suppose since it is allowed to vibrate, it will create or it will produce a wave. Alright, that wave is, suppose it is originating from this point. It goes like this. This is the wave. It goes like this. And here, since that is a rigid support, this wave is not able to move further. But what it will do is, it is getting reflected from this surface and it is coming back like this way, this way. So here that means two waves are there. One is incident wave, one is reflected wave, and they are superimposing with one another. Superimposing means they are overlapping with one another, forming a stationary wave. This is a stationary wave because it is confined between this point and this point. Clear? So that's what is written here, and moreover these two waves, certain characteristics of the two waves are same. Like they are having same amplitude, they are having same time period, because it is a part of same wave only, right? One wave is going, the same wave is again reflecting back. So their certain characteristics will be same. That is why they are effectively forming a standing or stationary wave. Now let us see the definition of stationary wave. Okay. So here I have written, when two progressive waves or of same amplitude and period but traveling in opposite direction. One was going like this, another one is coming like this. Okay, opposite direction with same speed, superimpose, they overlap. A wave is formed which does not appear to travel. The wave, that means the resulting wave, is not appearing to travel. It is confined between this point and this point. So that is called standing waves or stationary wave. Alright. So now the example that I gave you just now, that there is a string, The string is disturbed, it is forming a wave. Now see, if this is a string attached between this point, is it necessary that it will go like this? How many crest and trough it is forming? Is it necessary that it will form 3 crest? Here it is forming 1, 2, 3 crest, 2 trough. Not necessary. It may form more also. So depending upon the number of crest and trough formed in a stationary wave, it is classified into few modes. What are those modes? That one we will discuss in the next topic. Okay. So let us see here. Next topic I have written, standing waves in a string fixed at both ends. Now see, if the string is fixed at both ends and if it is disturbed, a tension will be created in the string. Tension means it's a kind of force, and the string has some mass. Suppose the mass per unit length of the string is mu. Mass per unit length of the string is how much? It is mu. T is the tension. Then velocity of the standing wave thus produced, V is equal to root over T by mu. This one derivation is not there. You just remember the formula. Velocity of a string wave. This velocity is formed for in which case? In case of a string wave, and the formula is root over T by mu. T is the tension of the string. Mu is the mass per unit length of the string. Alright. Now we will discuss about different modes formed in the string. So first one is, the first one that I have written here, this one, fundamental mode or first harmonic. This one, fundamental mode or first harmonic. So see here, the string is attached between this point and this point. And how the wave is formed? And one thing you remember, when this type of standing waves are formed, this point where the displacement is 0, these are called nodes. This is also, this point also, nodes. And this point where the amplitude is the maximum, this part, these are called antinodes. Okay, nodes and antinodes. So since the string is attached between two rigid support, this will be one node, no displacement, another node, no displacement. Here this region is antinode. Okay, this is a fundamental mode, means the string can vibrate in this way, basic way. Again the string can vibrate in this way also, this way. That is the second mode. Again the string can vibrate this way also, right? This is the third mode. So there are different kind of vibration can be seen there. So first we will discuss about the fundamental mode or first harmonic. Here you can see, this is the length of the string, L. Since each time we are taking the same string, the length of the string will remain same in all the modes. Okay. Then wavelength. About wavelength, you remember one thing here. The thing is like this. Okay. This is one semicircle, right? One semicircle means how many waves are there? As I told you before, just at the beginning of this video, one complete cycle means one wavelength, lambda. It is half of a cycle, means wavelength is lambda by 2. Okay, that means here length of the string is equal to lambda by 2, half of a wavelength. And since it is fundamental mode, I have written here lambda 1 by 2, fundamental mode or first harmonic. So I have written 1. Now this lambda 1 is equal to 2L. Alright. Then just now I told you that velocity of a string wave is this one, V equals to root over T by mu. Then what is the frequency? The formula, V equals to what? The formula that I gave you already. V equals to lambda nu. So nu equals to what? V by lambda, right? V by lambda 1. I have written nu 1 because it is the first mode. Now nu 1 equals to v by lambda 1. Now v means which value? Root this one, and lambda 1 means 2l, right? So we got this formula. This is equation number 1. Next one, second mode. In second mode, the string can vibrate this way. This is the next possible mode. So if it is like this, node, antinode, node, antinode, node. Alright, how many waves are there? Semicircle, another semicircle, like this, no? Semicircle, semicircle. So it is forming one complete cycle. One complete cycle means one wave, lambda. So we can write here L is equal to lambda. But I have written lambda 2 because it is the second mode or second harmonic. Another thing, this second harmonic can also be called as first overtone. Then the third harmonic will be second overtone. Okay. Anyways, the process is same. Lambda, just like we did in the previous case, nu 2 equals to what? V by lambda 2. Here it was nu 1 equals to v by lambda 1. V will remain as it is, root over t by mu. Lambda 2 is L here, so 1 by L. This one I have modified a little bit. In the numerator and denominator I have substituted 2. Why? That one we'll discuss later on. Just same thing only, no? In the numerator and denominator, if we multiply it with 2, the thing will remain same. So that is why it is just modified. This is given equation number 2. Next one, third mode. So this is the next possible mode of vibration. So here you see how many waves. Semicircle, semicircle, one complete wave, another half wave. So it is 1 plus half lambda. 1 plus half lambda means it is 3 by 2 lambda. That means here length is equal to 3 by 2 lambda. But I will write lambda 3 for third mode. From this, lambda 3 equals to 2l by 3. Then nu 3 will be how much? V by lambda. Same formula, this one only. Like this, like this. V by lambda 3. So V is this value and lambda 3 is this value. So it comes like this. Alright. Now see, in this 1, 2 and 3, except this one like 1, 2 and 3, rest terms are same. Only here we have 1, here we have 2, no, above, and here we have 3. So if you take the ratio of nu 1, nu 2, nu 3, what will be that ratio? 1 is to 2 is to 3. 1 is to 2 is to 3. That is why I made it 2 by 2, so that we can easily get the ratio. So in this way, for n number of n modes, we will get the ratio like 1 is to 2 is to 3 till n. Okay, so there may be question that from this part, like show the or find the ratio between the different modes, find the ratio between the frequencies of different modes of vibration in case of a string or in case of a string wave which is fixed between 2 points. Okay, so I think this much is clear. Then in next video we will discuss about different modes of vibration for organ pipe. Thank you.